So today we are actually going to go over a method to solve linear systems by hand that will then inform us on how to program the same thing so that we can do the same thing on a computer. Difference is that in terms of solving things by hand, we will solve only 2 by 2 or 3 by 3 systems. Anything larger, even 4 by 4 already could be quite a bit of work to solve. So we will avoid doing by hand anything really bigger than 3 by 3. That's what computers are for in this one. So basically, before we can actually go and program the algorithm, we actually need to know how to do it without a computer. So I am going to open up my so-called sketchbook that allows me to project things. There we go. And 310, and then lectures, 6 blank notes. All right, so we can actually go to 13. All right. So the method we are going to go through is due to Gauss, so it's quite old, and it's called Gaussian Elimination. Somebody is very happy about it. I'm glad to hear that. Okay? So Gaussian elimination is essentially a solution procedure and what it does, it has 2 steps. First step is transform a linear system of equations that you're trying to solve into an upper triangular system. Do we recall what upper triangular means? Form. So if you remember, we had on that worksheet, one of the problems was upper triangular. So basically everything below diagonal was 0 in that matrix A. Lower triangular would be the other way around.
Wouldn't that be the echelon form?
Echelon form, you move it forward and you have only diagonal elements. Echelon forms. So that's actually when you actually start solving. And then second part, we will do it by then solve upper triangular system by back substitution. And that's again what we did last time when you have an upper triangular form. You start at the very bottom because that equation is very simple and you kind of move up. So we will now review that, so you should come back into focus. Okay? So let's do a super simple example, 2 by 2. Start easy. So my system is x1 plus 3x2, 2x1 plus 4x2 is equal to 6. Excuse my ignorance, who are we playing tomorrow? What's the color? Baylor's green? Alright, green shirts. Do we have any? We don't have many green shirts. I have 2 over here. Alright. Alright. So green shirt number 1. what is my matrix of coefficients? So we said that this is equivalent to AX is equal to B. What is my matrix of coefficients A? So this is same as AX is equal to B. What is A? Do you have a green shirt? There's a green shirt right there. 1, 3, 2, and 4. Yes. So basically, this here is the same as 1, 2, 3, 4, multiplying x1, x2, right? And then is equal to which vector on the right-hand side, second green shirt? 5, 6. So I can actually see when I do matrix multiplication, this is 1 times x1 plus 2 times x2 is equal to 5, which is the same as this first row here. 3, 3, 3, 3, yes. That was testing whether you pay attention. Of course. Okay? And then when I multiply the second row of A and this column x1, x2, I will get 2x1 plus 4x2 is equal to 6, right? So these two things are really equivalent. This is just a matrix form of the system. Now the way we will actually start transforming, I have this step 1, transform a linear system into a triangular one. I'm going to form what's called an augmented matrix. So I'm going to literally start with augmented matrix. I'm actually just going to put together A and B. And I'm going to divide them with sort of an imaginary line. And it's really just for our own eyes. So basically my augmented matrix for this will be 1, 3, 2, 4. And the last column of it will be 5 and 6. So this is my B and this is my A. And the reason for doing this is I'm going to transform these equations. And I know already that just because I'm multiplying an equation by a number, adding it to another equation, I'm not necessarily doing anything to the solution itself. So the solution of that system will be the same as the starting system, but I'm going to make that system easier for me to solve. And a system that is actually easier for me to solve would be one that has a 0 here, right? Because all I would have then is 4 times x or whatever coefficient times x2 is equal to something else, right? So I'm going to transform this, okay, by basically multiplying my first row by an appropriate number and subtracting it from the second one. Okay. So what would that appropriate operation be? Right, so I could essentially replace this by 2, I'm going to refer to this as 2 first and second Roman numerals. And I'm kind of making Roman numerals to be separate from the numbers themselves. So my first row and second row. So I'm going to simply replace by 2 minus 2 times 1. Okay? So I ran out of green shirts, but Baylor goes with green and yellow, right? There's a green hat. There's a green hat. Good. Great. And he has yellow on his suit. So if I do that, what will I get? So I will actually go by entire first row. So first row remains the same thing. So I have 1, 3, 5 here. So basically minus 2 times 1 plus 2 is 0. Minus 2 times 3 is minus 6 plus 4 is negative 2. Minus 2 times 5 is minus 10, plus 6 is minus 4. Okay? Well, that's it. This is actually what I call upper triangular form because this is a very small system. My diagonal is simple, and the only one coefficient that I have below diagonal is this one, and now it's 0. Okay? So this is upper triangular form. And I am continuing my attack on yellow shirts, but we only really have one that I can see. So, hello. We'll have to come up with our next week competitors as well after we run out of Baylor colors. So now I'm actually going to solve with back substitution. So what is the easiest equation that I can solve in this system? So basically this last one, right, is very simple. It's minus 2x2 is equal to minus 4. So my x2 is equal to 2. So start by solving. So solve the very last equation. And then use that in the equations up. So I have only one equation up. Okay? So basically I'm going to plug that into this first equation, or my first equation has actually remained the same all along. So basically x1 plus 3 times 2 is equal to 5, which gives me x1 as minus 1. So this is a very small system, but this approach where I start solving from the last equation back up, every time successively just employing more and more knowledge that I have, this is called back substitution. Okay? That is essentially it. Now we will move on to a 3 by 3, so I'm just going to have a longer procedure. So here, in terms of these coefficients, I'm going to work harder to make all of the coefficients below diagonal 0. So this process, basically what it does is the target is all coefficients below the diagonal should become 0. So essentially you do what's necessary to make that happen. And then it's easy to apply back substitution. Now how do I know that I actually arrived at a correct solution? How do I verify? Since you wanted to speak. Yes. How do I verify that x1 is equal to 1 and x2 is equal to 2? How do I know that I didn't make any mistakes?
When you plug it in the original equation.
Precisely. So I will go to first one, for instance. So x1 plus 3x2 is what? It's minus 1. It should be 5, is it? It's minus 1 plus 2 times 3. It's minus 1 plus 6. It's 5. So yes, it should be, but don't let that make you imagine that it is, right? So when you verify, you gotta doubt it first, and then you verify. All right, let's move on to something a little more complex. And open another page. All right, so let's go with the following example. So it's 3x1 plus 2x2 minus x3 is equal to minus 1. Oops, 2. 6x1 minus 6x2 plus 7x3 is equal to minus 7. 3x1 minus 4x2 plus 4x3 is equal to minus 6. Who are we playing next week? Take over. There's a tailgate party. Okay, red color. Shy on the opponent's colors. We have one red shirt. All right. So she's texting. She's texting her friends to text the stick. All right. Let's check this. All right. So how do I now? Let's go through the same procedure. What is my augmented matrix for this? -1, and then I have -1 here, right? There we go. All right. So this is my augmented matrix. And now my target is to eliminate below diagonal. So this is below diagonal, this is below diagonal, this is below diagonal. Okay? So I'm going to work systematically. And I'm going to first eliminate coefficients in the first column. Okay? So in order to eliminate 6, what should I do? Okay, so basically I can do my second row plus 2 times first, right? If you want to fit into the mold of what I did just before, it's actually really the same as minus 2 times first, if you want to deduct something. But basically this works. And technically you can, when you're solving by hand, do whatever combination works. I mean, technically this is the same as -2 minus 2 times I, or so forth. It's going to be just multiplied by a -1. Not a big deal when you're solving equations, okay? So it's when you're programming that you have to be careful and always consistent. If you're just doing by hand, you can find what works, okay? So let's do this. What is this? So my first row remains the same. And my second row becomes what?
0, 4, 5, -9.
Is it 4 or -2? All right. Okay, now it should be correct. And then what will I do with my third? Gotta switch to blue. There's a sea of blue here. All right. So let's go by blue. In the very last row. You wake up your friend. What am I going to do with this one? I can just add them up. So basically my 3, I'm going to replace this by 3 plus 1. So again, this is my 1, 2, 3. So what will I get when I do that? Of 3, -7. All right. Okay. So my next target is this position here. The number has changed slightly, right? But I'm going to use now this position. So I call it the position that I'm using to actually gauge which coefficient to multiply with what or what to do. This is called a pivot position. Okay? So based on this, these two numbers, this is what I want to eliminate. Okay? My next blue is right there. So what am I going to do with this last two? Okay, so basically I'm going to replace that works 3 minus 2. Okay, so what will I get when I do that? I'm going to quickly write these again. So what will I get in the last row? -2. So note that these first two positions that I eliminated, nothing happened to them because I had a 0 here, okay? So I did not mess up what I did before. And that's why it's important to go in order and start from the first column and work this way. Okay? And now I'm actually It is. Okay, so now I'm actually in a position to use back substitution. Okay, so I'm going to work from the bottom. So what will I get my next? All right, so based on the back substitution, so I'm going to actually do, so this is my second step. Okay, minus 2x3 is 2, and therefore x3 is minus 1. So then my next blue shirt is in this row. So now what am I going to do with the second equation? Yes. So that what will I get? Yes? Plus 5 times, you already did it. I'm going to get a 0. Okay. So that's my second one, right? So minus 2x2 is equal to? So x2 is 2. Okay? And now I have two solutions that I'm going to plug into the first one. So can you do that for me? Okay. So this is minus 2, minus 6, right? There we go. So this is our solution. Okay. So can somebody quickly verify that we got the correct solution? So pick, let's go with first equation. Minus 3 times 2 is 6. Plus 4 is minus 2. Minus 1 is minus 1. So we're good. Okay? So just quick check. Minus 3 times 2 plus 2 times 2 minus 1 times minus 1 is minus 1. So that checks out. I should technically check the other equations, but at least 1 is enough. Okay? All right. That is Gaussian elimination. Now we will actually go through some trouble with Gaussian elimination. So let's actually see, so this, let me switch my, so this is a very nice procedure, except when it doesn't work and I have to do something. So here's an example where it doesn't. It's called partial pivoting. So let's assume that my system is 2x2 plus 3x3 is equal to 6. 4x1 plus 6x2 plus 7x3 is equal to minus 6. 2x1 minus 3x2 plus 6x3 is equal to 2. So what is the augmented system? Here's blue right there. So what is the augmented system for that?
0, 2, 3, 6, 4, 6, 7, -6, 2, 6, 2.
Okay. So now, if I want to use this, so technically my target positions are this, this, and this to eliminate. Is there anything I can multiply my first row with to get rid of 4?
4? Oh, no.
No. So I have a 0 there, so that's a problem. Now what could I do to fix this?
Swap. You can swap it there.
Everybody's wearing blue shirts today.
Oh.
Fantastic. All right. So, indeed. So I'm not changing the system if I swap, right? So I'm simply going to do that. So essentially, cannot use this first row to eliminate coefficients. So we have to swap rows. And it is customary for numerical error reasons to find the coefficient that is the largest here and work with that. So basically I can just swap 2 and 1. For instance, 1 and 2, but just a comment, typically we find a row with largest coefficient. To do that. So basically when I do that, I'm going to have 4, 6, 7, minus 6, 0, 2, 3, 6, and 2, minus 3, 6, 2. So I already have one of the desired coefficients as a 0. Okay. So I can work on my third one. So what will I do to eliminate this position here? Sure, so you're saying multiply by 2, right? And please, whenever you're solving this, tell me on the side what you're doing. That works. So, and you wanted to subtract that from 1? Or what did you? So what did you want to do?
That works too. I mean, that's one of the ways to do it.
Either way works. So you wanted to do it this way?
Sure.
He's agreeable in general. All right. So, I mean, a lot of things work. I could also say 3 minus 1/2 times 1. Okay? So a lot of things work. It's just that I don't want to deal with 7/2 here. Okay? So avoid that. So just a comment, minus 3 plus 2, or 3 minus 1/2 1, it all works. If you're solving by hand, it all works. It doesn't work if you're programming. So if you're programming, you have to do the same thing every step, or else you don't know how to program. Okay? You can't use a for loop otherwise. Okay, so what do I get when I do that? Can you help me? 400, that's true. So I'm gonna just copy first 2. What's in the last row? Okay. And the last one I have to work with is I have to eliminate this position. Okay. And in order to do that, what does the council motion suggest? So 6 times this. I could go to the
You
next.
can do that.
Yeah, he just wants to talk today. He can't help it.
6 times 2 plus.
That works. And then plus 3. Okay. So when I do that, I'm actually going to do it on the same page so I don't lose track. 4, 6, 7 minus 6, 0, 2, 3, 6. And here I will get a 0, which was the target. What will I get here? And here? It's a 36 here, plus 10. Mm-hmm. And 46 is good, because x3 is 2. All right, so this is ready for back substitution. Okay. So back substitution. (23x3) was 46. So x3 is 2. And then I will go to my previous row. My next blue shirt is right over there. So my previous row, which is not here, but you probably have it in your notes.
It's 2x2 plus 3.
Oh, yeah. Everybody's talking over everybody today. That's all right. It wasn't clear which blue shirt. So my x2 is? Yes. And finally, the last one now you can go. Yes? Okay, so the first equation is 4x1 plus 6 times x2, which is a 0, plus 7 times x3, which is 2, is equal to minus 6. Can you solve that for me? Minus 20, so x1 is negative 5. So my solution vector is minus 5, 0, 2. So if I was showing it as a vector, is minus 5, 0, and 2. Okay, so now we know what to do if I actually encounter a 0 and I have to save myself. We know that if I have a system of equations and I just swap the places of two equations, I'm not changing the solution to the system. So those are the things that I can do. So just as a recap, things that we can do, we can always multiply one of the equations with some number, and I'm not going to change the solution. Of course, if you multiply by 0, then you killed one of your equations. That's not good. Okay? So don't do multiply by 0. And also if I do what's called a linear combination of two of the equations, so basically I can always replace one of the equations with a linear combination of others, okay? And typically involving that one. And then I'm not going to actually change the solution to my system. So those are the things that we can do to make the solution easier. Now we can also often, you will not always, when you're modeling, so technically the way you encounter these systems of linear equations is you will model a system and you will actually get these parts to be your fluxes or something else in your system. And we're going to get to examples like that next. But sometimes it's not always clear what coefficients should be. Okay? And then you can actually evaluate what the solution or how will the solution look like depending on those coefficients. So here's a small example of that. So let's actually see. Your task is to find all solution possibilities based on coefficients C and D in the following system, it's a small system, 2x1 plus x2 is equal to c, and 4x1 plus dx2 is equal to 7. Again, right now it's abstract what these coefficients are, but let's say that you were modeling something and this is what you got. Okay. Well, you can still apply the same principle. So there is an augmented matrix here, which is 2, 1, c, and 4, d, 7. Okay. So what will I do to actually just perceive its solution? So I still want to eliminate this 4 here. So he wants to replace this by 2 times 1 minus. Is that correct? Or the other way around? That's fine. Okay. So what will you get? So now the next thing that I would do here to actually solve my system, I would start with back substitution. And I just have to guard myself with problems. If I actually had a 0 here, that could be a problem. And if I have a 0 here, then for this to be actually plausible, I should have a 0 here as well. So first thing that I have to consider in this, okay, is the following. Is everybody ready to? Okay. So first thing, assume the case if d minus 2 is equal to 0 and what was it, 7 minus 2c is equal to 0 at the same time. And the reason why I'm doing it separately is that I don't want to divide by 0, right? So if they're both the 0, so that's basically when b is equal to 2 and c is 7 over 2, okay? In this case, my last equation is essentially 0 equals to 0, so that doesn't help me, that's always true. Right? So I have 0, 0, 0 for all coefficients. So the second equation doesn't contribute to the solution. Okay? And the only one that actually I have is the first equation. So all I have is 2x1 plus x2 is equal to c, which is 7 over 2. So x2 is 7, 2 minus 2x1. And x1 is a free parameter. So any pair x1, 7 over 2 minus 2x1 works. So that's a whole line of solutions. Okay? So this is infinite number of solutions in the form x1 and 7, 2 minus 2x1. So if I look at it as a vector, right? No, what did I do? So we typically say that x1 is a free parameter, right? So for any parameter x1, I will get a solution. So all of them are on a geometrically on a line, because this is actually equation of a line. This is y equals to 7 half minus 2x, right? So geometrically, and that's okay. So just my solution is not as constrained as it would be. Now what happens in the second case if my d is minus 2 is equal to 0, so d is equal to 2, and c is not 7 over half? Okay? So I have 0, 0, and then something non-zero. What does that tell me? No solution. So if I'm the engineer who came up with the system, I gotta go back and say, well, this is not a plausible system, so we can't have this. Okay? So this is actually pretty good. This gives me quite a bit of freedom. Okay? The second option is a no-no. So this is impossible. System, since I cannot have 0 equals to something non-zero. Okay? So there is no solution. So that's in the case where my lines are so-called parallel, right? If I was trying to look for intersection of two lines that are parallel, I don't have a solution. Okay? And then finally, if d minus 2 is different from 0, whatever that is, I can simply divide by it, right? So then basically my x2 is equal to 7 minus 2c divided by d minus 2. And x1, I plug into the first one. So what was it? 2x1 plus x2 is equal to c. So x2 is, well, c minus 14 minus 4c divided by d minus 2. It's something of that form. Lazy today, it's Friday. But it's a unique solution, okay? So these are typical possibilities. Even though this is a small system, this is basically what you could get. The only difference in larger system, you could actually get multiple rows that are rows of zeros, in which case you might have more than one free parameter. Okay? But other than that, these are essentially the cases that you might have as you're solving for a system. So this first one is also sometimes called underdetermined system that doesn't have a unique solution. All right. So starting next time, we're actually going to come up with some systems and actually form them.
Just the very last